Good evening, everyone. Today is our uh, ninth classes, right? In this week, we will be talking about some questions related to your solid state physics, okay, which is related to your like packing fractions and let's say lattice constants and so on, okay. So before we move ahead, okay, you can always refer to these books, okay, for especially for these topics, okay, your solid state physics, your solid state physics by Kittel. Right. So this is um, all the details. Most of the details are here. Okay. So in this case, we will be solving problems, which is mainly based on the topics from uh, Kittel. Okay. So in this sections, we will be talking mostly, as I've said to you, like mostly on your density of states and your lattice constant and so on. Okay, so maybe I can just write a few formulas to you. Okay, if it is helpful. Okay, otherwise these are also taken from that textbook Charles Kittel. Okay, so any formulas which I solve in the problems, you can easily get it from the textbooks. Okay, these are not that new topics to everyone, okay. More or less is already what maybe might of you have already learned a lot about this also, yeah. Okay, so maybe I can start, or maybe I can start now. Okay, so if you look from your week 9 assignments, okay, there are 5 problems. Okay, there are 5 problems. One is related to your graphene. Second is related to your packing fraction. Okay, so packing fraction. Third is related to your velocity of sound. Okay, how do we find out the velocity of sound? And last two is related to, suppose if you have your EK diagrams or the energy to your wave vector, you can, how do you find out the group velocity? How do you find out the effective mass of the anti-electron and so on? Okay, so I can start. Okay, so if you look at the questions number one, if you look at the questions number one, it is related to a graphene, which says that graphene has 6 effective atoms per unit cell. Okay, so graphene has 6 effective atoms. Remember this one, with the unit cell area given by 3 root 3 divided by 2 a square. Okay, if the magnitude of the Fermi wave vector is 3 Armstrong. Okay, this is inverse. Okay, because uh, k is related to inverse of your distance, so that is why it will be a 0 inverse. Determine the value of a. So if you look at these problems, what is already given to you is, n, which is the number of atoms per unit cell is 6. Area is also given to you, okay, which is equal to 3 root 3 by 2 a square. Okay, area is given to you. Then what else is given to you? K, which is the Fermi wave vector, is given to you 3 Armstrong inverse. Okay, so see, if you have to find out if if the number of atoms is given to you and also kf is given to you, Then main important is you have to relate this to how does they are related to one another. So remember, the graphene is a two dimension. Okay, it's not three dimension, it's a two dimension. So if you look at it, okay, if you look at it, how does the density of states, if you look at it, if you talk about 2D density of state, 2D density of state, what is happening? You will have equal to area of your Fermi circle divided by area of each state, right? So the area, you know, is will be equal to pi, and in terms of pi kf square, instead of pi r square, this is in the k space, so you get pi kf square divided by the area of each state. This is in two dimensions, so we have seen last class where 2 pi by l is the area of, I mean, is the length of each state. So if it is a two dimension, 2 pi by l whole square, right? 2 pi l is the dimension in one, is one unit along x or along y along z. So if it's a three dimension, we get 2 pi by l to the power cube, or if it's a two dimension, we have to divide by 2 pi by l whole square. Okay, now if you substitute it, you get l square kf square by 4 pi, right? So now how does the density related to this? So number of electron, it will be equal to n equal to g, if it, in case there is a degeneracy, into the density of state, L square kf square by 4 pi, right? And n by L square equal to, let's say, n, which is the number of electrons per unit area in this case, right? Per unit area or per length square. So we have what? N equal to g k f square by 4 pi. Okay, but for graphene, what happens? G equal to 4. How do you get G equal to 4? Is because spin degeneracy equal to 2 and valley degeneracy equal to 2. So there are 4 possible states, okay, degenerate states. So in that case, your n will be equal to 4 and 4, G is equal to 4, so 4 in G and 4 pi in the denominator, 4 and 4 will get cancelled. So ideally you will get something like kf square by pi, or simply kf equal to root over of pi n. Okay, this is how you can calculate how does k and n are related to one another. So according to these problems, we can write again, so we can follow this one. So for graphene, the relationship, I would say, the relationship between electron density n and kf is what? N equal to g, like I have written, let's take this relation, let's say equation 1, you take this g, but instead of g I will write gs, which is the spin degeneracy, gv, which is the valley degeneracy, kf square divided by 4 pi. Okay, so what happens? Gs is actually the spin degeneracy, which is equal to 2, and gv equal to 2, or you can write n is equal to kf square by pi. Okay, I can write here, let's say equation number 2. Okay. So now you have the relation between n and kf. So how do you get n now? Kf is already given to you, n is also given to you, but here you have to calculate n per unit area. So graphene has 6, that means n equal to 6 effective atoms per unit cell. Correct? Graphene has n equal to 6 atoms per unit cell, and with area A equal to 3 root 3 by 2 A square. Therefore n, which is the number of electrons, let's say, or we can say here, assuming that each carbon atom contribute one electron, contribute one electron, contribute one electron, then assuming that each carbon, okay, assuming that each carbon atom contribute one, then electron density will be called what? N will be equal to the number of electrons 6, or I will write first the formula here. N is equal to N divided by the area, right, which is equal to what? N is equal to 6, area will be equal to 3 root 3 by 2a square, which is in fact equal to 4 divided by root 3a square. Okay, so you see here you get N based on the formula, which is equation 2, and also N equal to capital N, which is the number of or the number of effective atoms per unit cell, divided by the area, you get the electron density. Okay, so if you compare this equation 2 and equation 3, what do you get? You will get Kf, isn't it? So comparing 2 and 3, what happens to 2 and 3? You have N on the left hand side, you also have N on the left hand side, then you have what? Kf square, it will be equal to 4 root 3 a square equal to Kf square by pi. Since both the left hand side are the same, so we can use the right hand side also to be the same. Okay, so now you know what is N. You substitute the value of N, and from here you can get what is a Kf, which is a so a square, okay, so will be equal to 4 pi divided by root 3 Kf square. Okay, why I'm using this? Because what is the question? The question is you have to find out the value of A. Okay, and here if you look at it, you know the value of A, and Kf also you know, isn't it? Because Kf is equal to 3, right? So therefore A is equal to root over of 4 pi, take the square of it, and then we can get some root over of 3 Kf square, which is equal to 2 by Kf, and this will be equal to 4 pi by root over of 3. Okay, so now from the number density relation to Kf, you know what is the approximate lattice constant. Now once you do this, Kf is already given to you, it's already given to you. Kf is equal to 3 Armstrong inverse. Then what happens? A, you can just substitute 2 divided by 3 root over of, sorry, this should not be 4 here, there should not be any 4 here, it should be equal to pi by root over of 3. If you do this, implies that A is approximately 0.89 Armstrong, because what is that? This is A Armstrong inverse. Remember, the unit of Kf is equal to 3 A naught to the power minus 1, okay, which is equal to 3 Armstrong inverse. That is why you get 0.89 Armstrong. Okay, so this is a very standard problems where if you have to find out the lattice constant, so given N and Kf, so you find the relation of the density of states. Okay, from the density of states that we have talking last class, we can relate between the number of electrons, or the density of states, and with the wave vector k. So once we know that, we can easily calculate what is the lattice constant. So this is the standard the problems. Okay, fine, I hope you understand. So in these problems we didn't introduce anything that much. We introduced only the density of states, and then we find out the relation between N and Kf, and then we find out the lattice constant A based on the values that is given to you based on Kf and N. Okay, that's it. So now we will move to the second problems. Okay, what are there in the second problems? So let me write the questions. So in question number 2, you have for NaCl, okay, sodium chloride, for NaCl, it is given radius of sodium ion is 0.98 Armstrong, okay, comma, radius of chloride ion is 1.81 Armstrong, okay, and atomic mass of sodium is 22.99 AMU, and atomic mass of chlorine is 35.45 AMU, okay. Calculate the packing efficiency and density of NaCl. Calculate the packing efficiency and density of NaCl. Okay, so before I solve this problem, just give me 2 minutes. Okay, just give me 2 minutes break. I'll come back in 2 minutes, please. Yeah, sorry for that. Okay. Okay, so if you look at the questions number 2, what is happening in question number 2 is that it is given to you that it is sodium chloride. Okay, there is an Na, and there is also there is a sodium, and there is also chloride. Okay, so and what is also given to you, radius is already given to you. Both the radius of sodium and both the radius of chlorine is given to you, as well as the atomic mass unit. Okay, so what you need to come out is the packing efficiency and the density. So you have to know what is packing efficiency. Okay, packing efficiency is defined as the volume occupied by the atoms to the volume of the available unit cell. Okay, so if I write the packing efficiency, PF is volume of, let's say I can write volume of atoms occupied by the atoms divided by the volume of unit cell. That means, suppose if you have a unit cell, one unit cell, and how many number of atoms we can fit in that. So that is the packing efficiency, how much we can stack different atoms into each unit cell. Okay, so if you have to draw about the structure of the NaCl, okay, it might be a little difficult to it might be a little difficult to visualize it. Okay, but you can easily check in the, like, in most of online. Okay, you will see the how does Na and Cl are arranged. So if I can draw like very roughly, you have, this is like a simple cubic. Okay, very roughly. So what happens is that, suppose this is a cube, so how does Na are arranged? So Na are arranged 1 here at the edges, 2, 3, 4, 5, 6, 7, 8. That is one thing. And also on the face, that is this face, one more atoms here, one more atoms on this area, one more atoms on the side, and this is also one more one more zero, one more Na, and finally this way. So that means Na are arranged along the edges of a cubic as well as also at the face. So that is why it's a face cubic. phase cubic crystals. Okay, so that means not only that, this is only Na, and also Cl is also arranged alternatively. I can write here, 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 and so on. Okay, so I suggest you go to online. Okay, if you look at it, you will see a better picture of how Na and Cl are arranged. Okay, this is just a rough drawing. Okay, that means just remember that your NaCl is arranged in the phase cubic phase cubic center. Okay, NaCl is a phase cubic center. So yeah, so that is how it should be. So now if I try to find out how many number of atoms are there in this unit cell, you have to find out how many number of atoms in there. So first of all, you have Na per unit cell. Na per unit cell, if you look at it, what happens, these atoms is shared by 8 order atoms or 8 order unit cells, right? So 8, there are 8 atoms, 1 2 3 4 5 6 7 8. Talk only the edges is shared with 8 order unit cells, right? So each atoms is shared by 1 by 8, that means it's shared by 8 unit cells, and there are total number of 8 atoms, plus these atoms at the phase. Okay, at the phase we get, there are 6 of atoms, there are 6 atoms of such case of such atoms, and it is shared also with 2 unit cells. So that is why if you look at it, the total number of Na per unit cell, it will be equal to 4. Okay, similarly chlorine or Cl per unit cell equal to, again, 8 into 1 by 8 plus 1 by 2 into 6 is equal to 4. Therefore, I can write Z consists of 4Na plus 4Cl, which is equal to 4NaCl. Okay, so if I want to show you this, how is it? This is Na, this is Na, this is Na, these are the number of atoms, and here this is chloride, this is also chloride. Okay, this is also chloride, and so on. Okay, and so on. So I suggest you please just check an online scientific illustrations of NaCls. Okay, you will have a clear understanding how Na and NaCl is very easy. That means Na and Cl are arranged in a phase cubic centers with Na and Cl occupying the octahedral sites. Okay, so if I want to solve this problem now, what happens that in a unit cell, just remember that in a unit cell, how many number of atoms are there, that you need to find out. Okay, so in our case, in each unit cell there are 4 NaCl. That means there are 4 Na and 4 Cl. So if you take the whole NaCl structures, you have 4 NaCl per unit cells. Okay, that is what you need to do. Now, okay, so now you know how many number of atoms are there per unit cell. Why we need to know this is because when you calculate the packing fraction, remember, why do I have to calculate this? Because is the volume occupied atoms. What atoms here? Atoms is Na and Cl. So it will be volume of Na plus. But how many Na plus are there? That is what you have to find out. There are 4 Na plus. Plus volume of, again, 4 Cl minus, divided by volume of unit cell. Why you need to know how many number of sodium and how many number of chlorine is because you need to find out the volume of each of them. Okay, that is what you that is why you need to find out how many number of Na and how many number of Cl are there. Okay, so also what is also very important here is that if you derive this formula, what happens, this is volume. Say what is the formula? We can get something like 4 into volume of Na will be equal to 4 by 3 pi r Na. You can write Na plus Q plus, again, there are 4 Cl, so 4 into 4 by 3 pi r Cl cubed divided by the volume of the unit cell is what? Simply A cube. Because why I'm saying A cube? Because this is length A, right? This is also length A. So in a cube, you have the volume will be equal to A cube. Okay, so So in such cases, what you need to find out? Suppose if you have to find out the packing fraction, what you need to find out, you have to find out what is the radius of NA, what is the radius of CL, and what is the A. Okay. So but it is given to you the radius, not the lattice constant, right? So you have to find also A. What is A? Radius is already given to you, right? Radius is given to you, but not A. So what is the H length? This is also called as A, is also called as H length. Okay, H length. H length A equal to, if you look, it will be equal to twice R of Na plus RCl minus. Okay, if you look at it, this length A is equal to twice the radius of your Na plus twice the radius of your Cl minus. Okay, that means you get the total distance from one edges to the other edges. Okay, so that's now it's easy to R of Na plus is already given to you, is 0.98 Armstrong, plus R of Cl minus is already given you 1 plus 81 Armstrong. So what you need, what you got is around 5.58 into 10 to the power minus of 8 centimeter. Why? Is because Armstrong is equal to 1 into 10 to the power minus 10 meter. Okay, so so once you get the H length A, you can substitute back in the same equation 1. It's easy now. Equation 1 will become, equation 1 becomes what? Or packing fraction equal to, you can take common 4 and 4 you can multiply, so we can take common, we can get sub 16 pi by 3, you can get R of Na plus whole cubed plus R of Cl minus whole cubed, right, divided by A cubed will be 2 R of Na plus R of Cl minus whole cubed. So now it is direct. You can just substitute what is the radius of Na. You substitute what is the radius of Cl. You also substitute this Rna plus of RCl minus. You already got from here, which is equal to A, right? Which is equal to A. Then you can easily get the packing fraction. So you can substitute. So let me just do this. So A, if you do 2 and 2 to the power cubed, you will get 8. 8 with 16 will get cancelled. Okay, so we get 2 pi by 3. First of all, sorry, I should write it. You get 2 pi by 3. Okay, and R of Na cubed plus R cubed remain the same. R of Na plus of R of Cl minus whole cube remain the same. So you substitute what is R of Na and R of Cl. Why? It's because R of Na is already given to you. R of Na is given to you in this problem. R of Na is 0.98 Armstrong, 1.81 Armstrong. So I'll just substitute back there. So it's equal to 2 pi by 3, 0.98 Armstrong plus 1.81 Armstrong, and also 0.98 plus 1.81 whole Armstrong into 100. Okay, remember there is also Armstrong unit there. Okay, but they will get cancelled one another because this is cubed, and this is also cubed to the power cubed. So they will get cancelled one another. So if you calculate this one, you'll get approximately 66.26%. Okay, you can cross check, but this is approximately 66.26 Armstrong. Okay, so this is the packing fraction. So how do you calculate the packing fraction? You can calculate the packing fraction based if you know the volume of the total number of atoms divided by the volume of the unit cell. So volume of unit cell is is A cubed. So in order to know A cubed, you need to know what is the H length A. Okay, and other than that, radius is already given to you. Okay, now second part of the problems. So second part of the problem is you have to find out the density. Okay, I hope you know this formula. Density equal to Zm by rho A cube. Okay, so the relation between your density, your molecular weight, as well as your density and the H length are given by this formula. Okay, so if you look at this formula, what happens is you have to calculate density. Z you already know, which is equal to 4. Molecular weight we have, molecular mass, you have to find density. Sorry, this is not density. Sorry, this is Na, or I will write it right. Na. This is your Avogadro's number. So Z equal to 4. Okay, so okay, for those who just joined just now, okay, let me just uh, uh, repeat, okay, what we have done. Yeah, so we are trying to find out, we are trying to solve the problems number 2, and which is related to how do you calculate the packing fractions. Okay, if you want to calculate the packing fractions, what you need to do is you need to find out what is the volume occupied by the total number of atoms to the volume of the unit cell. Okay, so Z equal to 4, then molecular weight equal to M Na plus M of Cl, right? Because it's NaCl, so you have to find out what is the molecular weight of Na plus of Cl. So this is given to you 22.99 plus 35.45. This is equal to 58.44 gram per mole, right? And Na is also, which is equal to 6.023 into 10 to the power 23, okay, mole inverse. Okay, then A is also, you already know, calculation is 5.58 from here. A you already know, which is equal to 5.58 into 10 to the power minus of 8 centimeter. Yeah, so you know the value of Z, you know the value of the molecular mass, you know the Na, which is the Avogadro's number, you know A, which is the H length, then you can substitute all these numbers here. You substitute all those numbers here. That means I will get rho equal to 4 into 58.44 gram per mole and 6.023 into 10 to the power 23 mole inverse. And remember, this is in terms of, because I'm using in terms of the CGS unit, so you get 5.58 into 10 to the power minus of 8 centimeter cube. Remember, if you convert this terms of kg, right? If you want to if you want to convert this molecular weight in terms of kg, then remember you also have to convert everything in terms of the SI unit. That is, even A also has to convert in terms of meter if you calculate grams in terms of kg. So, but here in this case, I use only CGS unit. I mean grams and centimeters. So we get rho equal to, if you solve, 2.234 gram per centimeter cube. Right? Otherwise, if you use, and you can either convert these molecular weight in terms of kg also. That is also fine. But remember, you also have to use this in terms of meter, not in terms of centimeter. Okay. So this is the problems number 2, which quickly tells you what is the how do you calculate the packing fraction, which is pretty straightforward. Or formula which calculates what is the volume of the atoms occupied divided by the total volume available. Simple as that. Okay, and if you want to find out the calculation of density, we can use this and the formula. Okay, so next we will calculate. Before I move to question number 3, let me solve first question number 4, which is more or less similar. Okay, which is more or less similar to these types of problems. And yeah, so, and in question number 4, it is given to you the energy wave vector relation. Okay, and from there you have to calculate what is the velocity, what is the value, a constant value in which the electron receives maximum. You have to calculate what is the energy difference between the top and bottom of the energy band, and also the effective mass of the electron. So let me just remind you that from the EK relation, that is the relationship between your and the energy and momentum K, that you can calculate almost many things. Okay, many quantities, I will just say, quantities you can calculate. Okay, so if I write a formula, if I write the questions, is that the energy wave vector dispersion relation. Okay, what is the dispersion relation? It's the relation between the frequency omega with the wave vector k. For a 1D crystal with lattice constant A is given by Ek is equal to E naught minus of alpha minus of 2 beta cos of k, where okay alpha and beta and no okay are they're overlapping integral respectively. Okay, so the question number A that it is asks is what? Determine the value of k. What is value of k here? Is so determine the value of k in which the electron velocity is maximum. So the question is determine the value of k in which electron velocity is maximum. Okay, sorry for that. So we have to do we have to determine the value of k in which the electron velocity is maximum. So what is this electron velocity? Okay, I hope in the all some previous few classes we were talking about the group velocity, right? The group velocity. So in case of here also is the group velocity we are talking about is given by 1 by h cross dE by dk. Okay, so if you look at it, Vg is equal to d omega by dk, right? So omega, you know, E is equal to h cross omega. So d omega will be in terms of energy is equal to 1 by h cross dE dk. Okay, this is the group velocity that we have derived previously. So now 1 by h cross dE dk. So from there you will get what is the velocity of the electron. So dE by dk, what will happen? If we calculate, we can type d by dk. E will be equal to E naught minus of alpha minus of 2 beta cos ka. Right, so we have to differentiate the energy. We have to differentiate, you know, the energy that is given to you. So these are all constant. These are E naught is constant, alpha is constant, except this term you have to differentiate in terms of k. So what you need to do is you can differentiate d by dk of this one will get minus of 2 beta cosine. It will be negative sign, so this will get positive. You get sine ka into a. So the total will become 2 beta a sine ka. Right? So now Vg equal to 1 by h cross into this 2 beta a sine ka. Right? Because dE by dk is 2 beta a sine ka. So if you multiply with the with 1 by h cross, you will get what is known as your group velocity. Now what happens is that the question is determine the value of k for which electron velocity is maximum. So when this is maximum, it is maximum because this is constant, depends on your sine ka. So if sine ka is maximum, then your velocity is also. Otherwise, if sine is minimum, then your Vg is also minimum. So when it is maximum, sine ka. Okay, what is the minimum and the maximum value of sine is minus 1 to plus 1. So the maximum will be sine ka is equal to plus 1, because the range of the sine function that it can take is from minus 1 to plus 1. Right, so sine of ka will be equal to 1. Let me just write it properly. So sine ka is equal to 1. So what happens? You get sine ka equal to 1, which is equal to sine ka, which is also equal to sine of pi by 2. right? Because pi by 2 sine of pi by 2 is equal to 1, so sine and sine will get cancelled, so we can get something like k is equal to pi by 2. See, you see that the velocity will be maximums only when k is equal to pi by 2a. That is, wave factor is equal to pi by 2a. Otherwise, other than that, the velocity will be minimum. Okay, so if sine ka is equal to 0, then the velocity will be the minimum. Okay, so from here, you can easily calculate that what is the value of k in which your velocity is maximum. So you have to, since there is a sine term there, so you have to put the sine term equal to 1. Okay, then you will be able to calculate what is the k term in which the velocity is maximum. Okay, question number B. Okay, what is the question number B? Question number B is determine or calculate the energy difference between the top and bottom of the energy band. Okay, so determine the energy difference between the top and bottom of the energy band. Okay, so what does it mean here? We have to determine the energy difference between the top and the bottom of the energy band. So if you want, if somebody asks you what is the top and bottom, that it depends upon the k value, right? So so ideally, I would rather say I will solve that problem in this way. Okay, so first of all, the extrema of the energy band occurs when dE by dk equal to 0. So you know that this is the extrema of any energy band is given by what? The derivative. So dE by dk should be equal to 0. Okay, so that is the extrema. This is the extrema condition. Now what happens to dE by dk equal to 0? If you look at it, dE by dk equal to 0, what will happen? dE by dk equal to 0, that means this happens only when sine ka equal to, or k is equal to 0, or k is equal to pi by a. So these occurs when k, or when sine k of a equal to 0, right? Because if you look at it, dE by dk depends upon the sine ka. So if your sine ka equal to is equal to 0, that means your if dE by dk equal to 0, that means your sine function has to be equal to 0. So sine ka will be equal to, here will be equal to sine of n pi will be equal to either a is equal to 0 or k is equal to plus minus of pi by, because sine of pi by a, which means what? Sine of k into a is k is equal to pi by a, so a and a will get cancelled, so sine of that will be equal to 0, or k itself is equal to 0. Okay, so there are two values of k in which dE by dk equal to 0. That is what I'm trying to say. Okay, there are two values, k is equal to 0 and k is equal to pi by a, for which dE by dk equal to 0. Okay, now since we have to find out what is the energy difference, we can do in this way. At the bottom of the band, what happens? K equal to 0. So if k is equal to 0, we get E minimum equal to what? Equal to E naught minus of alpha minus of 2 beta, and instead of cos of Ka, we get cos of 0. So you get E naught minus of alpha minus of 2 beta, right? Because since cos of 0 is equal to 1. Okay, now whereas at the top of the band, k will be plus minus of pi by a. Then what happens? See, when E maximum will be equal to what? E naught minus of alpha minus of 2 beta. Sorry, maybe I can write it a little better here. Alpha minus of 2 beta, and what? A cos of pi by a, right? Cos of pi by a will be equal to cos of pi will be equal to E naught minus of alpha plus of 2 beta, right? So the energy difference that E will be equal to E maximum minus of E minimum. So if you take this one as equation 1, if you take this 2 as equation 2, then you know E naught and E naught will get cancelled. We will get something like E naught minus of alpha plus of 2 beta minus of E naught minus of alpha minus of 2 beta. So E naught will get cancelled, alpha and alpha get cancelled, but delta E will be equal to 4 beta. Why 4 beta? Because here minus 2 beta, minus and minus will get cancelled, will get become plus, so we get 2 beta plus of 2 beta will go to 4 beta. Okay. So fine. In this problems, what we have seen is that we use the EK relation, and once we use the EK relation, we can find out what is the velocity, which is given by a group velocity of the electron. Then you also talk about your your energy difference between the bottom and the top band. So that is given by your dE by dk equal to 0. So in such cases, this is given by k equal to 0 and k is equal to pi by a. Now the last one is your effective mass. So how does your effective mass also changes? Okay, that is the third question. The third question is derive the effective mass of the electrons at both the top and bottom of the conduction band. So I will not write the questions. I will just write question number 3. Sorry. Yeah. So we have to derive the effective mass. So when I say the effective mass means you have write effective mass equal to h cross square d square e by dk square to the power minus of 1. Okay, this is your effective mass. So now dE by dk you already know. When we have to calculate the group velocity, you already know. So dE by dk you already know, and you just need to add the value of k at the top and the bottom. So from there you can get what is the effective mass, okay, both at the top of the band and bottom of the band. So when you talk about the bottom of the band, you are talking about k equal to k is equal to 0, but when you talk about the top, you have to k is equal to pi by a, because this is what we got, right? dE by dk equal to, we get sin ka should be equal to 0. If sin ka should be equal to 0, then k equal to, or k is equal to pi by a. Okay, now so we'll just differentiate again. So d square e divided by dk square equal to dE by dk or d by dk. So dE by dk you already know from the first formula, which is equal to 2 beta a sin ka, and this is equal to, if we differentiate, a square cos of ka. Right, differentiate it again. So you get d square e by dk square. Now what happens? M star will be equal to h cross square divided by 2 beta a square cos of ka. Okay, so again, m top, m star top, what happens here? K equal to 0. So k equal to 0, we get m star is simply h cross square divided by 2 beta a square. But when you talk about m star bottom, we get k is equal to pi by a, which is exactly equal to m star is equal to minus of h cross square divided by 2 beta of a square, because cos of 0 is equal to 1, but whereas cos of pi is equal to minus of 1. So you get m star at the top is h cross square divided by 2 beta square, whereas m square at the bottom, I can write here m top, whereas m bottom is completely the negative of your m top. Okay, mass at the top of the band. Okay, so this is the end of your questions number 4, that which says that, okay, given the EK relation, okay, so yeah, suppose if the EK relation is given to you, what you need to find out? You need to find out what is the velocity. So you can use the E by dk relation. Then again, if you have to find out what is the energy, again you use the k is equal to 0 for the bottom of the band, k is equal to pi by a in this case for the top, and then you calculate the energy difference between the top band and the bottom band, and finally you have to calculate the effective mass. Okay, so fine. Next questions we will talk about question number 3, which is also the similar to this relation, but it is given in terms of your omega and k, that is the frequency and k relation. And for that you have to find out what is the velocity of sound. Okay, so if you want to specifically derive these problems, okay, you can look from Kittel is diatomic chain. you will see that the relation between omega and k that will be derived, and that in this case is already given you the final problems, okay, or the final not the final problems, the final expressions, and you have to use that to calculate what is the velocity. Simple as that. So I can write the Farnon dispersion relation for a 1D for a 1D lattice with masses m1 and m2 is omega square. This is a frequency. Q is a wave vector here, okay. Don't misinterpret Q as a constant, okay. In the previous case we are talking K as a wave vector, but here, since there is also a constant term K, so this is a constant, not a wave vector. This is a constant, remember, okay. It's a constant, not a wave vector. So you can write 1 by m1. That's why we represent your Q as a wave vector here. 1 by m1 plus 1 by m2. Remember, this is a diatomic change, so there will be two different type of masses. Here 1 plus minus 1 minus of 4 m1 m2 by m1 plus of m2 whole square and sine square qa by 2. Okay, so this is exactly what I was talking to, that the expression after you solve the diatomic change, you will end up in this expression. So this expression contains both acoustic mode and optical mode. Acoustic mode is omega square q with the negative sign. That means this one. Okay, whereas the positive sign corresponds to your optical mode. So if you want to solve out what is the acoustic mode or the velocity of time, you should be talking about the acoustic mode. So in acoustic modes, you in this plus minus sign, that here inside the bracket, you will be talking mostly only the negative sign. And also importantly is that for sound, what happened? Wavelength is very, very large, right? So omega frequency should tends to 0, and also q should tends to 0, because q is what? Is a wave vector. Q here is the case is wave vector, so we get 2 pi by lambda. K is equal to 2 pi by lambda. So if lambda is very, very large, then your wave vector should goes to 0, and also your frequency should tends to 0. In that case, you get omega square q is equal to what? This remains the same, k m1 plus of m2 divided by m1 plus of m2, right? This is remain the same one. Instead of positive negative, you are talking about negative, because this corresponds to your acoustic mode. So then you can write 1 minus of 4 m1 m2 by m1 plus of m2 whole square sine square qa by 2. Okay, so now since for long wavelength, what happens? Q, as I told you, q tends to 0. Then if q is very, very small, then what happens? This sine of theta is almost equal to theta. Then therefore the first one, sine square qa by 2, this term here would be equal to what? Would be equal to q square a square by 4, right? 4. Why? It's because sine square qa by 2, this you can take this term as theta, so tan theta is almost equal to theta, so sine square is equal to theta square, so we get q square a square by 4. Okay, then now you solve this relation inside the bracket. So maybe I can name this as some constant, as some constant x. So constant s is equal to 4 m1 m2 by m1 plus of m2 whole square q square a square by 4. Okay, and what else do you need here? You need 4 and 4 will get cancelled. You can write something like on this side, something like m1 m2 q square a square by m1 plus of m2 whole square. Okay, so x means this term here. I can represent this one as x. Okay, maybe some. I can represent this one as x then. Okay, so x then. So you can write this one x. Then what else? If you look inside this integration, you also 1 minus of x. Sorry. Maybe here I can rename it. This one is not here. I can rename only this one. This one as an x term. So now 1 minus of x integration square root is approximately equal to 1 minus of 1 by half x. For x is very less than 1. This is from your Taylor series. Okay, Taylor series allowed you to find an estimation, not an estimation, or an approximation of 1 minus of x. You can expand it in 1 minus of 1 by 2 x, provided your x is very less than 1. Right, so now you know x, you know this integration now, you know, and you can easily calculate it what is the omega in terms of k. So now if I write completely, it will be omega square q is will be equal to k m1 plus of m2 by m1 plus of by m1 m2, correct? And you get 1 minus, instead of that square root you can write 1 minus of that term, m1 m2 q square a square by 2 m1 plus of m2 whole square. So if you solve this one, negative and negative will get cancelled, so you can write something like k a square by 2 m1 plus of m2 q square. So omega square, then omega is equal to 1. Omega will be simply omega is equal to simply root over of k a square by 2 m1 plus of m2 q square. If you remember correctly, your your velocity of sound is equal to omega divided by k, or in this case we'll get something like q. Remember, there is no square here because it has been cancelled out. So omega by k will be simply equal to a. We can take it outside because anyway it's a square term, so you can get something like a divided by 2 m1 plus of m2. Okay, so if you need to find out what is the velocity, you can just solve what is the expression, which is omega and k, and find out what is and find out the ratio of your omega with respect to q. Remember, q here points out that it is a wave vector. Okay, not a constant. The constant term here, k is in fact a constant. Okay, this one. Okay, so and that's also given to you. I think it's already given to you that a is a lattice constant and k is a force constant. Okay, so can you give me just 2 minutes, please? Okay, I'll join back in 2 minutes, please. Okay, thank you. So we will continue the last problem for today. Okay, that is your question number 5. Okay, and then we can, if you need any extra tutorial, we can also talk next week. Okay, for today's sessions I will solve up to one more problem, okay, related to your assignment. Okay, if any one of you wants more questions to be solved, okay, we can always conduct some 1 or 2 more hours for a tutorials, okay, that I can solve it at that time. Okay, so for now I want to finish your next assignments. Okay, I mean your question number 5 assignments. So in the question number 5 it is given that, okay, given that your Debye temperature of diamond, okay, Debye temperature of your diamond is 2000 Kelvin. Okay, Debye temperature of a diamond is 2000 Kelvin. Okay, calculate the mean velocity of sound. Okay, so knowing the Debye temperature, you have to calculate what is the mean velocity of your sound in a diamond. So calculate the mean velocity of sound in diamond. Okay, and given to you, okay, the density rho is equal to 3500 kg meter cube, whereas your atomic mass is 12 AMU, and also interatomic distance A is given to you to be 1.54 Armstrong. Okay, so you can look at the questions, okay, yourself. Okay, I have just cut short. So given the density is given to you, atomic mass is given to you, the lattice constant or the lattice spacing is also given to you, 1.54 Armstrong. And what do you need to calculate? You have to calculate what is the frequency. The first one is calculate the mean velocity, and the second one is estimate the frequency of the dominant mode of vibration. Okay, so you have to find out what is the velocity and what type of modes is dominant at this temperature. Okay, so now solution. You can look this problem, okay, again from this Charles Kittel, I mean from your Kittel solid state physics. Okay, it will be there related to your the Debye temperature, and I will write the relation here that the Debye temperature I can represent as something like theta d is related to cutoff frequency omega and mean velocity by the relation theta d. This is the Debye temperature is equal to h cross omega d by kb. So this relation comes what? Your h cross omega is equal to kt, right? They are a similar form. Okay, so now this will be equal to h cross divided by kb, and omega d, which is the cutoff frequency, is in fact equal to Vs 6 pi square n to the power 1 divided by 3. Okay, so Planck, this h cross, kb, you have to find out what is the velocity, and you have to find out what is the value of n, right? So n here we know what, so theta d is given to you to be what, 2000 Kelvin. Density is also given to you to be 3500 kg meter cube, and also m, which is the atomic mass, is also given to you to be 12 AMU, which is equal to 12 into 1 AMU is equal to 1.66 into 10 to the power minus 27 kg. So 12 into 1.66 into 10 to the power minus 27 kg, you will get 1.99 into 10 to the power minus of 26 kg. Okay, so in this case, I have just insert that what is the value of the Debye temperature, density, and the molecular weight. And if you need n here, if you look at this problem, if you look at this formula, you know h cross, you know kb, you have to calculate what is the velocity. That is, you have to calculate theta d, you know, and you need to know what is the value of n. So n is equal to what? N is equal to, okay, or your density is equal to number into your atomic mass, or n is equal to rho by m. So rho, you know, is 3500 kg per meter cube, and here also m will be equal to 12 amu, which is equal, in this form we got 1.99 into 10 to the power minus of 26. So kg and kg will get cancelled. You will get something 1.75 into 10 to the power minus of 29 meter cube. Okay, so once you know the value of n, right, then you just insert all the equations in your equation star, and you can easily calculate what is your velocity. So now velocity is what is equal to kb theta d by 1.99 into not 1.99, kb theta d divided by h cross squared 6 pi square n to the power 1 divided by 3, right? So kb, you know, kb is equal to 1.38 into 10 to the power minus 23. Theta d, you know, which is equal to 2000 Kelvin. Okay, h cross square is also 1.05 into 10 to the power minus of 34 whole square into 6 pi square also, you know, and n you already calculated. N is equal to 1.75 into 10 to the power 29, right, and then to the power 2 by 3. Doing this, okay, and solving it, you will get approximately into 10 to the power 4 meter second meters. Okay, you can cross check the calculation. Okay, you can cross check the calculation, and you can get an approximate of the velocity of sound to be around 10 to the power 4. Okay, so for a diamond at this temperature, for a diamond at a temperature of 200 Kelvin, what is the velocity you are expecting? You are expecting a velocity of around 10 to the power 4. That means what is the velocity of sound at that temperature is approximately equal to 10 to the power 4. Now the next question is estimate the frequency. So estimate the frequency. So I will use this formula, estimate the frequency, estimation of frequency, we get h mu d is equal to kb theta d. So your frequency mu d is kb, kb theta d divided by h, right? Kb theta d by h. I'm using the same thing, but in this case I'm using your original formula, h cross omega is equal to kbt, or h mu frequency is equal to kb theta d. So kb is 1.38 into 10 to the power minus of 23 into 2000 divided by h, because 6.6 into 10 to the power minus of 34. This will be approximately equal to 4.1 into 10 to the power 13 hertz. So this is your frequency that you are talking about. Okay, and so using and also it's also given to you, what is also given to you, if you look carefully, it's also given your lattice parameter to be 1.54. Okay, so given it's already given to you that your lattice parameter is equal to 1.54, or lattice constant. I was saying lattice constant is 1.54, which is equal to 1.54 into 10 to the power minus of 10 meter, right? So how will be the frequency? The frequency will be equal to mu equal to Vs, which is the velocity of sound, by 2a, right? Why? Is because lambda is equal to 2a. So frequency is equal to Vs by lambda, which is equal to Vs by 2a, which is equal to Vs is given to you 11993. How does the velocity of sound? Is already given to you, right? It's 1.2 into 10 to the power 4. I can write it here, approximately 1.2 into 10 to the power 4 divided by 2 into a is given to you to be 1.54 into 10 to the power minus of 10, right? So these, your dominant frequency is approximately, I can write 3.89 into 10 to the power 13 hertz, right? Alternative. Okay, so it's also given to you that your A is given to you 1.54 Armstrong, and also use your condition lambda is equal to A, and your frequency here is simply the velocity of sound divided by lambda, right? So Vs is equal to mu lambda, right? Vs is equal to mu lambda, right? So lambda is equal to 2a in this case. So frequency and Vs, you already know, you have already calculated from the first sections, divided by 2a. Okay, so from there you can easily calculate what is your frequency. So in these problems, in this problems, what we did is we find out what is the mean velocity of sound, and also what is the frequency, and other than that we also have seen what is the packing fraction, and if EK relation is given to you, what is the group velocity, what is the effective mass, right? So these are all standard problems, formula based, I can say formula based. Okay, once you and if you want to go behind how those formulas are obtained, you can get help from this Kittel's book. It is there. Okay, how does these formulas are obtained, and all these problems are mostly a formula based problems. Okay, so I will stop here for today. Okay, so if you have any questions, feel free to mail me, and also we can also organize maybe one hour or 2 more hours to solve any other alternative problems, okay, if you want. Okay, for the time being, I want to stop here for today, and this I have completed all the 5 assignments, and all the 5 questions of your assignments. Okay, so I hope it will be helpful for you. Okay, so I will upload all the details also in the drive. Thank you so much.